What are common Rankine cycle problems in power plants? Imagine a power plant trying to turn heat into electricity, but facing unexpected hurdles along the way. That's what happens with the Rankine cycle in real-world conditions. This cycle is the core process in steam power plants, where heat from burning fuel turns water into steam, which then spins turbines to generate electricity. But many issues can pop up that affect how well this cycle works. One common problem is pressure losses in the system. In theory, the boiler and condenser should operate without pressure drops, but in reality, pipes, valves, and heat exchangers cause some pressure to be lost. This means less steam pressure reaches the turbine, reducing how much work it can do and increasing the pressure in the condenser. These pressure drops make the cycle less efficient than expected. Another issue is turbine blade erosion and wear. Steam turbines often handle steam that contains tiny water droplets, especially if the steam is wet. These droplets can hit the turbine blades and cause erosion over time. This damages the blades and shortens their lifespan, which means more maintenance and less efficiency. Controlling condensation in the condenser is also tricky. The condenser needs to turn all the steam back into water before it is pumped back to the boiler. If the condensation isn't complete, it creates a mixture of liquid and vapor, called two-phase flow. Handling this mixture in pumps is difficult and can cause operational problems. Proper cooling water supply and pressure control are essential to keep the cycle running smoothly. Efficiency is limited by the temperature difference between the heat source and the heat sink. If the boiler doesn't operate at very high temperatures and pressures, the cycle can only reach a certain maximum efficiency. Usually, modern plants that operate at supercritical pressures can get efficiencies around 40 to 42%, but lower temperatures mean less efficiency overall. Making improvements like reheating steam or preheating feedwater adds complexity and cost. Reheating involves expanding the steam in stages, then reheating it before the next expansion. Regenerative feedwater heating uses some of the exhaust steam to warm the water before it enters the boiler. While these methods boost efficiency, they also require careful design and extra equipment, which increases costs. Maintaining a good vacuum in the condenser is vital. A strong vacuum lowers the pressure at the turbine exhaust, helping it do more work. But if cooling water supply drops or the water temperature rises, the vacuum weakens. This causes the back pressure to increase, which reduces the power output. Materials also play a role. Operating at very high temperatures and pressures can cause metal parts to degrade or develop thermal stresses. This limits how hot and high pressure the boiler and turbines can run, and means advanced materials and regular maintenance are needed. Finally, environmental factors like fouling, corrosion, and scaling can block heat transfer surfaces, making the cycle less efficient. Startup and shutdown procedures also cause thermal stresses that can damage equipment over time. In short, issues like pressure drops, blade erosion, condensation challenges, temperature limits, cycle complexity, vacuum maintenance, material stresses, and environmental effects all impact the performance of the Rankine cycle in power plants. Understanding these problems helps engineers find ways to make power generation more reliable and efficient.